So listen, thanks again for that nice presentation. And I think we'll move on to our third, our final, but last but not least, comes from Western University, and it's part of the 3-university partnership that is Advanced Manufacturing Consortium, or AMC. So speaking will be Gleb Meirson, and he's going to talk about smart automated high-performance composite manufacturing. And just by way of introduction, Gleb is he actually received his undergrad and a master's degree training at Technion in Israel, so he comes with a very high pedigree. Worked in industry for a while, and then he moved on in Canada to do a PhD at Western. He stayed at Western and now joined the Fraunhofer Project Center, which is a very, very impressive large-scale composites fabrication facility. And he's a research engineer leading activity in the field of fiber reinforced plastics. And I should also comment that our group collaborates directly with Gleb and his team in the automotive crash structures composite manufacturing area. So that's quite interesting. So Gleb, are you all set to go?
Yes.
Okay, so if you'd share your screen, Gleb, and take it away whenever you're ready there, please. Thank you.
Thank you. Can you see my screen?
Yeah, it's just coming up now. Yeah, looks good.
Perfect, great. So hello everyone. So my name is Gleb. I'll give a talk about smart automated high performance composite manufacturing. So we're located in London, Ontario, and our facility FPC is a joint venture between Western University and Fraunhofer ICT in Germany. The center started as ICT in Germany was receiving more and more requests from North America, and they felt that they couldn't help the clients properly because of the time difference and the geographical difference. And so they decided to open a daughter company in North America to serve North American market. And so we're basically here to fill the gap between the European knowledge and North American knowledge, to transfer the knowledge from Europe to North America for composite advanced manufacturing materials. We have some very impressive technologies at our center. So we have both thermoset and thermoplastic capabilities. On the thermoset side, we have HPRTM machine, which stands for high pressure resin transfer molding. We have direct sheet molding compound machine, which is the only one in the world actually. We have a thermoset injection molding machine. We have thermoplastic injection molding machine, thermoplastic long fiber thermoset direct line, and tape placement, automated tape placement line at our facility. At the center of our facility, we have a 2,500 ton press. It's a very impressive piece of equipment. Its total height is probably about like as a 3-story building. It provides force of up to 2,500 ton. Usually when I give tours to the facility, I always say that this is a weight of 1,000 grown giraffes. So you can just imagine the force. Instead of the press, you can have 1,000 giraffes jumping out up and down on the mold. The movement speed of the press is also up to 100 millimeters per second, which is obviously very fast. We have the capability to heat the mold with both oil and water, and the total area of the press bed where the mold is 2 by 3 meters square. Just some of the very impressive projects that we done at FPC in the recent year. So one was this project, which was a partnership between Ford and BASF. And the idea was to replace the motor box from metal components to plastic components. So we molded the motor cover and the oil pan, and you can see here the reduction in weight by replacing metal to composite. So it was quite impressive. So while maintaining the same properties as the metal, so in case of motor cover, the drop was in 24%, and oil pan, the drop was in 33% weight. And this was done through injection molding. Another very interesting project we had was with Poisson, and the attempt was to replace Corvette magnesium roof with HPRTM roof frame from carbon fiber and epoxy. And you can see it was a very large consortium of all of those companies listed here. And the idea was basically to transfer the knowledge that exists in Europe for both mold manufacturing, material supply manufacturing, equipment manufacturing, and processing to North America. The results were also very impressive. You can see here the frame right in front of you, and it actually achieved 46 weight% savings compared to magnesium, while actually having better properties than the magnesium frame. So now the problem, if you wish, or the motivation for this talk and for our next development is that composites are, unlike metals, they are not isotropic materials. So you have different properties in different directions, and this requires very special treatment in terms of manufacturing, because if you design your part correctly, there is no guarantees that during manufacturing the properties, that the directions will stay the same. Basically, if you don't handle your composites well enough, things can shift. Composites are also not metals, they're very soft. So as you put it in the press, you can affect it. The material that you put in the press to mold is usually smaller than the mold, and so it's very important exactly where you place it in the mold. And so because of those reasons, you can imagine that automation is very important in it to get repeatable process and to get as low scrap rate as possible. And so we were receiving a lot of those questions in our center. So we've been doing quite a lot of projects, and oftentimes people from the industry would come and we would showcase them the process and we would make parts for them. But then the question would be, okay, so how do you automate it? How do you make now thousands of those parts and make sure that they're all the same? And this is actually a big problem. I mean, you cannot validate a part because each part might actually be different. So the validation has to be on the process level and not on the part level. And for that, the process have to be very repeatable. So it cannot be done manually. So we approached several automation robot manufacturers companies that exist in North America, and eventually we got to ABB. And I must say that they're really great people, very comfortable to talk with, very, very helpful. And they liked our vision and the vision of the center, and they agreed to give us a robot to conduct our research with it. And so the robot that we got at FPC is the IRB 6700 205-2.8, which basically stands to 205 kilograms load and 2.8 reach. And the research we are conducting with this robot is basically automation of state-of-the-art composite material manufacturing techniques. So we're taking the technologies that we have in the center and we're now trying to automate it instead of running it more manually. We're starting to implement machine learning and autonomous work for those technologies, and I'll explain later also why it's very important, and end-of-arm tool development for those processes. So the first process that we're looking at is liquid compression molding. And the way liquid compression molding works is you're applying resin on the fabric outside of the mold, and then you're transferring it into the mold, closing the mold to cure the resin, opening the mold and demolding the part. And the very good thing about this process is very fast. So this is something that the automotive industry really likes. It's a continuous fiber composites, so they're basically structural component. And so here, so the motivation is, like I said, a very fast manufacturing. So you can make parts in 2 minutes, button to button push. So it's getting close to metal stamping. But the problem in manual operation of this process is, just think about it. So first you have to apply the resin on the fabric. So the speed in which you're pouring the resin, the rate at which you're pouring the resin when you're doing it by hand would be different from trial to trial. The time that it will take you to apply the resin also going to be different, because sometimes the resin will shift to one direction or the other. You have to fix it. The time of the application, so when you pour your resin in a cup and then you go and pour, is going to be different each time. So again, even a few seconds would make a big difference in terms of the viscosity of the resin. Fabric placement, so now when we applied it and we're putting it into the mold, fabric is very soft, and with resin in it, it's very, how would you say it, lubricated, so it's very easy to fibers to change its orientation. So again, it's going to be different from time to time. Fabric temperature, because as the fabric would change its orientation, you have to try and fix it to the best of your ability while it's in the press. And so the fabric temperature will get up because the press is hot, and as each time is going to take you different time, the temperature will be different at the beginning. And most importantly, the application location of the resin on the fabric is also going to be different, because as much as we try to be the same, when you apply it by hand, it's not going to be repeatable. And so even by hand, you can do this process very fast, but then the question is, how repeatable is it? Are each part the same, or are they different? And so that's why automation is very important. So this is the process we started with, and you can see here a short video of this process running in our center automated way. So we have this end of the arm tool on the robot, so you see an automated preform movement to the robot. The robot is picking up the preform, and now it's going to move to the mix head, which is going to apply the resin on the preform and then move it to the press for molding. And as you see, everything is here because it's automatically made. It's very well controlled, and it's obviously repeatable. So now if we see some difference from part to part, then we know that this is just something that's inherent in material properties or just the process itself, but it's not due to how we perform the process. And so now you see this wet preform is moving into the press, into compression. Next process which we are looking for automation is Solvay's DDF, which stands for double diaphragm forming. So that's basically Solvay's solution for pre-preg molding for medium size application in a fast cure cycle. The way the process works is you have a preform, you close it in a frame in between films, then it's heated to heat up the film and the preform, moved to the press, closed in the press, molded, presses opens up, and the part is being removed. And the beauty about this process is, and that's what we hear from a lot of companies about liquid compression molding in terms of the problems they envision, is they say, okay, so you can automate everything, but how are you going to clean the mold? So you molded the part, great, now the mold opened, you took out the part, but you have all of that flash still glued in your mold, and now an actual person has to come and remove it before next cycle can begin. And this obviously makes cycles longer. In this process, this is not a problem because the pre-preg is in between two films, and the films basically act as a barrier between resin and the mold. So nothing sticks to the mold, so it's very easy demolding. The other good thing that it does is that a big problem we see in processes like HPRTM and LCM is the investment in the mold. So the mold in this process can cost up to $1 million very easily. And so for a medium scale application, if you don't want to do hundreds of thousands of parts, investing in a mold like that is very problematic. In case of a DDF, it's a fairly simple mold. It can be, again, aluminum mold. The problem that we see in aluminum used in liquid compression molding or HPRTM is resin sticking to the mold, and then there is actually no way of getting rid of it without damaging the mold. But in this case, because there is no direct contact of resin with the mold, it's not a problem, and you can use a much cheaper mold to make your parts. So it looks like a very attractive process. We already did some automated trials at FPC with it. Unfortunately, those trials are proprietary, so I cannot show you the video of that. Instead, I took a video from YouTube of DDF from Solvay's, how they advertise it, so you can see how it works at their facility. And again, their facility is located in Europe. And what our center tries to do is we're trying to bring those composite manufacturing technologies from Europe to North America, and to act as a bridge, or if you want, as a pipe of knowledge, transferring the knowledge from Europe to North America. So let's actually move to the actual process, which is here now. So you can see automated fabric cutting, then automated preform stacking. We actually had equipment like this at FPC for a while, and it wasn't used, so we disassembled it. And then this preform is moved automatically in the frame, in the molded, and now you can see how easy it is to demold it. You see, it just lifts it up, nothing stayed on the mold, very easy, fast demolding, and then you have your part. So it's a great technology for medium scale production. So far we talked only about continuous fibers manufacturing, but in this continuous fiber manufacturing there is also problems, probably even bigger problems than in continuous fiber manufacturing, because now you have another parameter that goes into the equation, and that's how you place your charge into the mold. So here you can see some simulations with it. So the top result is the experimental result, and the bottom three results are simulation results. And what we were trying to do is we were trying to mimic the warpage of the part in simulation to reality. And as you see, it actually was very difficult, and in the end we were not successful. And the reason is because things like warpage are extremely sensitive to initial conditions. And when you're doing the work manually, it's very hard to know what the initial conditions are if you need to know them accurately. So this is where, again, automation is required to get a repeatable process. So right now what we see in the discontinuous fiber parts is we see that when we make the parts and when we test them in mechanical properties, we see quite big derivation from part to part. And so when you design a part, you have to design it much heavier than what it should really be in reality. But the question is the reason because this is inherent in the process and the type of the material, this property derivation, or is this something that's related to the fact that we are just not doing the parts in a repeatable manner? So this would be our next thing that we're going to look in terms of automation of LFTD and SMC, and of course different end-of-arm tools have to be developed, and all of that work has to be done in order to do it. Finally, the final topic that we're looking at in the center is Industry 4.0. So it's already very big in Europe, but it's just starting in North America. And the idea is to look at industry as 4 different industrial revolutions, which in the first one, somewhat machinization was done, and then the second one, assembly lines were introduced, in the third one, robots were introduced, and now in Industry 4.0, we're talking about autonomous and machine learning systems. And so where we find this very important in our line of work is in recyclability and sustainability. So our center is strategically now dedicated to recycling, recyclability, and sustainability, and we're trying to look how our processes that we are running can be modified for that. So some things that we did so far is we have developed a feeder device for recycled carbon fiber into SMC and LFTD. And this is actually a very big subject everywhere, to try and use recycled carbon into SMC. And so far, people were not really successful in it much. And we hope that our solution is something that will attract the industry. And here, especially when you use recycled material, quality control of the process is very important. So part from part can be very different, and so we have to make sure that process is tracking all the necessary parameters, and that there is a sufficient control of the resulting part to see that it is according to specifications. Another interesting process for recycling is injection molding and LFTD. So there is a lot of recycling done for thermoplastic materials, and then those can be used in injection molding and in LFTD line. The problem is that even in a normal material, there is a huge difference, not a huge difference, but there is a difference in the same batch between different granules, because they cannot all be the same. Well, now imagine in recycled materials, those differences within the same batch are quite big. And so what this means is that you cannot just set your conditions in processing once and then run your process. But instead, from time to time, you will start getting scrap, and you have to keep adjusting your process to get good parts. And so here is what we want to implement here machine learning algorithms and automation so that the process can adjust itself to reduce scrap rate And here there are several approaches that we're trying to take. So one is principal component analysis, PCA, and there are other that we're looking at is neural networking. So thank you very much. This was some overview of what we're doing in our center and how it connects with AI and automation. I want to thank again all of our partners such as Diffenbacher and ABB for the great help that they're providing us in our work, and of course AMC for all the financial support that they gave us and keep giving. Thank you very much, and thank you for listening.
All right, Gleb, thank you very much. Can you hear me okay?
Yes.
Great. Okay, well, thanks for that very interesting talk. That was great. Just waiting, questions are just starting to come in. One question that does come to mind is, you're looking at LCM processes versus high pressure resin transfer molding. I'm just curious, how do you see the two processes one against the other? And then also, I guess this follow-up is, how do you see industrial adoption going? And again, maybe from a sector perspective even.
Yeah, so it's quite interesting. So the first company that started commercially implementing HPRTM is BMW in Europe. And over the years, they saw that a lot of the parts that they were making in HPRTM, they can make in LCM, liquid compression molding. And from this, and I think by now 80% of the parts, or even more, of what they're doing is liquid compression molding, is not HPRTM anymore. And the big advantage in liquid compression molding is it's faster. So, and it's faster for several reasons. Is you're saving the time. So in HPRTM, you have to inject your resin into the mold, while in LCM, you're applying the resin outside of the mold. So when you have to inject it into the mold, and this injection time is something that you have to add to your cycle time. So it's usually about 40 seconds that you're saving in liquid compression molding, because in liquid compression molding, you can apply the resin on the part while another part is already being cured in the mold. So you're saving this time. The other big advantage where you save time is that your mold can be much hotter. So as I said, injection time is usually 40 seconds, and you have to make sure that resin doesn't cure during those 40 seconds. So even if the chemistry of the resins allows fast cure and high temperature, you cannot fully utilize it because you cannot have the part curing before the injection is done. Well, in liquid compression molding, you don't have the injection, so you don't have this problem. So this is a very big time saver. So you can go from 5-minute cycle time in HPRTM to 2-minute cycle time in liquid compression molding. And that's why most of the parts are now in BMWs they are doing in liquid compression molding. The benefit of HPRTM is the complexity of the geometry. So if you have a complicated part, you will not be able to do it in liquid compression molding. Where is this border? Well, nobody really knows. This is one of the topics of our research, to try and find a distinct border from between which you have to go from LCM to HPRTM. Thickness is also another parameter. So there is a fairly limited thickness of about 2.5-3 millimeters parts that you can do with LCM versus HPRTM, where you can do very thick parts like 30 something millimeters. What's interesting about that is it seems like North American market is going to be able to skip the HPRTM variant completely. So North America was a bit late to the table for this process. And now when there's BMW is already successfully running liquid compression molding, we see some interest in the North American market for liquid compression molding as well. So it seems like we're here just going to jump this step completely and go directly for liquid compression molding. Another very good thing I think that's happening for this technology is the drone industry. So it seems like the automotive industry is very conservative, and they're not necessarily want to move in this direction, or at least they're not moving there fast. But where I think this is going to be utilized very heavily is in the drone industry. So the drone industry is now growing very rapidly. In the aerospace industry, this process could not have been used because of the high price of the molds, as I said earlier. So when you're not doing hundreds of thousands of parts, this process doesn't make a lot of sense because you don't need time, and the value of the mold just never going to pay for itself. But now with large amount of drones that are planned to be manufactured, I see this as another door through which this process can get in to North American market.
Interesting. I wouldn't have thought of that application. That's cool. Porosity in LCM, is it like air entrainment? Is that an issue, or is that kind of worked out now?
It's one of the issues. So one of the, I shouldn't say benefits, but one of the difference in HPRTM is that you're able to vacuum the air out of the preform before injecting. Well, in liquid compression molding, you cannot do that, because if you will apply vacuum in the same manner as HPRTM, while the preform is already wet, you're just going to suck the resin in those valves. So this is, I wouldn't say it's a problem. I would say that this is just an additional complexity. So when designing a mold, you have to design it in a way that as the resin flows through the fabric, it pushes the air out. In addition, there is actually an IP belonging to Huntsman of vacuum assisted LCM as well. So it is possible to do vacuum assisted LCM. It's just a bit of a niche. It's not, the IP belongs to Huntsman, so not everybody can do it, I guess. But if you're running the project with them, I'm sure that they will be more than happy to provide the IP, and the mold can be designed to use vacuum.
Okay, no, that's great. Thanks. Okay, well, listen, I think we're running out of time. So, Gleb, thank you once again for a very, very nice presentation. I appreciate that.
Thank you.
So, yeah, excellent. And so, with that, I think we've come to the end of our session. Just want to thank Nicola and Val for helping us out with the technical aspects, and thank our audience for sitting in on this, and of course our speakers once again. And I wish we could do applause, but it's not a very effective way to go. But certainly the sentiments there. We appreciate this. And with that, I'd like to encourage everybody to transition over to the joint session, and they'll be talking. One of the things we'll be talking about is actually where to get some money to do all this stuff. So that's rather important. From MyTax is one of the funding agencies. So with that, we'll call this to a close, and thank you once again for attending.